So this is on organic chemistry, the second discussion problem set. I am going to solve this problem very quickly on here. So the first problem is asking that, can you predict whether the leaving group, this leaving group, so you have to identify the leaving group, this is a leaving group, whether this will favor the SN1 or SN2. And this is a good leaving group. Because when they leave, and they became an H2O, which is a neutral, right? So when they are attached to it, this is a ion, but when they left, there will be a neutral, and that's a good leaving group. So this is a good leaving group. So they will love to leave like that, and then they become essentially cyclohexane cation, and this is essentially unimolecular. That means 1, right? And here is they asking SN1, so it's an SN1 is the answer. So first problem set is an SN1 is the answer, and I have give you a separate, more lengthy videos and to give you background information and so on. This is pretty much the similar problem. Okay, so this they said it's an elimination reaction. This is an alkoxide, which is a strong base. Okay, so this is a base, and they are trying to find the hydrogen from somewhere. And then you can see that here, the chlorine carbon is here. This having a little screen issues. The chlorine is here, and attached this carbon. And the elimination is essentially take the hydrogen from the adjacent carbon, and there is must be a hydrogen is. This is unavailable, which is available here. The other one, this alkoxide, will go and take it. Okay, and then this will form the double bond, and this will form having the leaving the chloride ion going away. So in a way, you are forming a double bond by taking the hydrogen away. That's an elimination reaction, which is a base is taking the H plus. Okay. But now the situation here is now I am going to make this the notation put a hold at the moment. Okay, so I know the hydrogen on the other side needs to go away, but then let's give a more three-dimensional representation of what's the projection looks like. So I'm going to look at from this. Let's do the Newman projection. And so if you do the Newman projection, so I will do the Newman projection here. So if I do this, the red one in the front carbon, so this red one, you do the dot. And then the one that on the plane, that's the one that is on the plane, so I would prefer probably use this one is one is pointing at the bottom. And then this one is a methyl, so this is a methyl. And the hydrogen, so because I use a blue color, maybe I can assure you this is a hydrogen that would need to be taken away. And then what I'm going to do is, let me use a black color then, the one in the back, oh no, the one in the back is this, and this one is essentially we are going to use a circle. And the one that this ethyl and this methyl are on the same plane. So if you're just using this plane line, they are on the surface of this plane. So I can usually say ethyl and the methyl are on the same plane. And with using this as a reference point, this is moving away. So you can think about chlorine on this side, and what is left over is on hydrogen. So that's a Newman projection. Just from here, you're looking at it. And then what you can see now is also the essentially kind of repertoire that I just saw it before. This is on hydrogen, and this is chlorine. So what I said before is this is a base, a strong base trying to take this hydrogen, and this double, so this is a base once more, base trying to take the hydrogen. And then they want to take this one to form the double bond. On the double bond, you can imagine the three-dimensional way. and then eventually this one has to go on. The chloride has to leave as a leaving group. So this one has to, okay, this one has to be the leaving group as a chloride. So then what is here? So I'm going to write it as a notation. This is quote unquote crowded. Okay? So this is what I mentioned about steric hindrance. Okay? So what they're going to do, because of this is the same notation that you are seeing here now. This is the same. Okay? And what they're going to do is they're going to essentially have a rotation. So what they're going to do is, instead of having the reaction happening this sigma bonding is free to rotate around. So because of those nature, this sigma bonding will try to rotate, and they rotate. Right? The sigma rotation. And then trying to make an effort that, okay, so what they did is they keep the back chlorine as they are, but they rotate the front protein carbon hydrogen, the sigma bonding, so that they can put the hydrogen on the opposite side. And then now you can see that you are in business, because of this bromine, not bromine, the base will go and take the hydrogen without being really bothered by the leaving group in a traffic congestion, right? This is a traffic jam. It can be avoided. They call it as an anti. So by doing so, it's a much better situation. So they are willing to do the sigma rotation to have a better conformation, okay? And the less steric hindrance, which is I mentioned here. So therefore, the answer here is going to be, so then now let's do this, right? So this is a front carbon, so then I'm going to color code it. That's a front carbon. The back carbon, if I want me to do, this is a back carbon. So I'm going to put the back carbon there, right? And then just finish the rest of them. So it's a double bond supposed to be formed because of the elimination reaction. And now you can see that methyl and ethyl are pointing in the same side up. So I'm going to put methyl. Oops, sorry. Methyl, ethyl. So CH3CH2. That's ethyl, and the methyl pointing at the bottom, and the hydrogen. So that's essentially the product of elimination product. So this time, unlike what I have just solved it before, this is in the opposite side, right? So this is what is a isomer? This is a trans isomer. But like I said, if you use a easy rule, the Eintgegen and Zusammen rule, if you look at the reference point, this has a higher priority because this is ethyl is bigger than methyl, and methyl is bigger than hydrogen. They are on the same side, so this is a Z isomer. So this is a case where you are seeing this too. So what I did here is essentially I went through solve the first problem and solve the second problem using the Newman projections to really have an understanding about 3D nature of compound. And then we are using this to have a better understanding. So Newman projection has been used. I think I have some issues with this program. Newman projection. And then we were able to predict this. So let me, I have provided here just as a recap for you to kind of the wrap up your learning about the organic chemistry sessions. So let me ask you this way. So here I have drawn the methyl iodide versus tertiary butyl iodide, and then I'm just asking you which will be fastest, okay? And I'm asking you, let's say for the SN1 mechanism, which one will be the fastest? And then there's let's just say this is an A and this is a B. Right? I'm just saying that I want to compare this these two compounds. Which one will react faster? And if you can you we approach. Oh, okay. And what are the other products? ROH and Cl minus. Oh, okay. There's a student who asked questions. Yep. So let me go back. But if you can think about which one will be the fastest one, you guys can post it in your answers on the chatting box. That would be great. I will finish up the rest of the question because this is the major product. And then what are the other products that you will see? Obviously the ROH is an alcohol. In the problem, I guess is an ethanol, and then will be a chlorine minus. And if you want to, so this one didn't show that is a sodium plus, so you can just say the chlorine minus here, or if it is a sodium there, then NaCl, and this will be an answer for you to do that. Has anyone thought about this? This is a very important if you guys to know this. Which will have a faster reaction. So SN1 means essentially leaving group has to be leave, and they make the carbocation, right? By itself. Right? Leaving group left by itself. And you ended up getting the carbocation. So anyone make a guess on that? You can type it. Have you ever seen this kind of problem? Yeah. So some students said yes, and yeah, Andrea, you are correct. And then the one student say the B is answer. Yes, and the reason is for the comparison of the SN1 mechanism, which will be the faster SN1 reaction. And the answers can be found from the carbocation stabilities, right? So this is a tertiary carbocation, and this is a primary carbocation. So this will be a stabler carbocation. So SN1 wise, which will be the fastest? This one, B, right? So the B is the fastest for SN1. This is an SN1 fast. So now let me switch the gears. What about the other one? SN2 fastest. How about that? So SN2 reaction, you need essentially what is the bimolecular reaction? You need essentially strong push by the strong nucleophile that is trying to push this iodine away. Okay, so SN2 reaction, you have a nucleophile, and this nucleophile looking for the essentially opportunity to attack, and this carbon is essentially positive charges. This carbon is positive charges. So this nucleophile is trying to make a bonding here with a carbon, right? And there's a nucleophile, strong nucleophile, which is let me say, what is an example of strong nucleophile? For example, CN minus. This is a strong nucleophile, right? Or alkoxide. That's also not only is a strong base, but it is also a strong nucleophile. Okay, so these are the example of the strong nucleophile, and they want to do the SN2 reaction. What do you think? That which one will be your fastest SN2 reaction? Can anyone try? The answer is the A will have a fastest SN2 fastest. Okay, so this is an SN2 fastest. Let me put a different. Why don't I do this? So SN2 fastest is this A. Can anyone see why what is a keyword for this? And it's because of the what is called the steric hindrance. The key for the why this is the fastest is because of steric hindrance. So when this hovering molecule of this nucleophile is trying to make a bonding with a carbon, this carbon has a three hydrogen is kind of the occupied space. We can compare that in this nucleophile trying to make a bonding with this. This carbon is quote unquote buried under these three bulky methyl group, right? So therefore, this is what they call, this nucleophile will experience steric hindrance. Steric hindrance is bad, right? And so they make the reaction will go slow for SN2 reaction. Okay, so that's the summary for that I want to say. And then this is the following table that I like to talk to you about this. So when you have some kind of compound, this is what I call this lone pair, right? Something that is a lone pair types, and you can have a nucleophile, you can have a base, right? And the nucleophile people write Nu, and this is and the base is something that with a B with lone pairs. That's unusual notation people take. And nucleophile itself means that you are already having an SN type reaction, whether it's a strong nucleophile or a weak nucleophile. And when you have a base, you're already saying that this is an elimination reaction. The reaction type is already defined as here. And when you have a strong nucleophile, and that means this one is just like I showed before. The strong nucleophile can essentially push the electron to the partially positive carbon, and an iodine is left. It's a bimolecular. It's more like a push and pull, or this more like a table. These two molecules has to collide to each other. So it's a bimolecular, so it's an SN2. So does here too. When you have a strong base, it is sort of the reaction happens at the same time. So this is a bimolecular reaction, is an E2 reaction. But when you have a weak nucleophile, right? When it is a weak, you have to wait until they kind of form this carbocation, right? So it's a bimolecular. The rate determining step is actually dissociation of leaving group, so that you can left with a carbocation. So that's here too. Though when you have a base, it's a E1 reaction. So you can kind of categorize that. And when another way to prove this reaction, whether it's a SN2 reaction, is a reaction rate is essentially K times essentially Rx times nucleophile concentration. Rx is an alkyl halide. Halide is a good leaving group, just like what you guys see here. Iodine, these are the alkyl halide, tertiary butyl halide, and that's how the reaction rate occurs. Whereas an SN1 reaction, essentially concentration nucleophile doesn't matter. It just by this concentration itself, the X is a leaving group here as an halide, and that's the reaction rate. And the E2, same region, is an Rx times, now instead of calling nucleophile, we just call BA base. When it's an E1, just a dissociation of halide from the alkyl halide, and that's what the rate has been occurs. Okay, so I will use a few minutes of remaining time to give the final 2 cents on this. One is, we talked about secondary carbocation to the tertiary carbocation, right? And this is based on the hydride shift and the methyl shift, and that's really the biggie in the organic chemistry. All of a sudden that you are looking at making a bond in a different location, because once they develop the carbocation, let's say based on the SN1 reaction mechanism, and the methyl or hydride hydride is trying to shift around to develop the more stable carbocation. But if I talk about carbocation, this is also another carbocation that you can see. This is let's say this is an R. And this benzene group attached to carbocation, this is what we call the benzyl carbocation. This is a very, very strong, is a very, very stable. Okay, it is actually even stabler than the one that's shown up on the right. So this is a benzyl, is also very, very stable, and the other one that is also known. You will learn more in the organic chemistry. This is on what they call the allyl carbocation, and so this is another categories that where you are seeing that they are all like a stable carbocation. If they want to do, I want you to expand your idea. It's not just about tertiary carbocation. It is all other types of the one. And another languages here is if you're looking at the let me see. This is a languages. If you look at that, and if there are two electrons here, right, in this bond, and then if this reaction is taking this everything here, okay, so this is a C. Let me just say methyl. If I do that, and then this will be, once again, they develop this tertiary carbocation. And from the perspective of just this step alone, right, chlorine minus. And this is, you can say this reaction as what they call heterolysis. This is, have you heard about the lysis? In the lysis means a kind of the dissociation, breaking apart. That's the scientist terminology, actually quite widely used in the biology community. Lysis means that you are breaking apart. So you are trying to break this one, but you are taking two electrons. Winner takes it all. Okay, so this chlorine take both two away. So this is not even the lysis. So that's why it's called the heterolysis. I think the Dr. Ma talked about that in the class. But if you think about the homolysis, so what that means is this one is now carbon. This carbon is actually radical, and chlorine is a radical. So what that means is before there's carbon-chlorine bond they are using the fish hook, and this one of the electrons are being taken out one by one. So it's halfway through the split, and you develop this. It's like an even split between the bond, the two electrons, and this is what is called a homolysis. Right. So this is a heterolysis, and you want to also familiar with this term. That is actually related to this is related to the E1 or E2 reaction, right? So here's I show the E1 as a reaction. Okay, so let me stop the